Today we're going to be talking about intermolecular forces. Okay, and you've done the reading on this, so I'm just going to go through these pretty quickly. So here's a compound HF, and we talked last time about how HF there's a pretty large difference in electronegativity between these two atoms, which means that we say that this is a polar compound. Okay, and another way of representing that is by saying that the electrons are not being shared equally, they're kind of sitting on the fluorine. Well, if hydrogen is giving up its electrons, that means it's going to have a partial positive charge. And we use the Greek letter delta, lowercase Greek letter delta, to mean partial. It's not a full positive charge because it's sharing those electrons, but it's partial charge. So we give that a little Greek letter delta with a positive. And the fluorine then would have a Greek letter that's negative. Okay, so that's one way of indicating that there's a spread in charge. By the way, the spread in charge is something that we call a dipole, okay, where there's an uneven distribution of charge. And another way of indicating that is with a crossed arrow, and we'll talk about the crossed arrow kind of a lot. All right, so here's my crossed arrow. It points from the hydrogen to the fluorine. And the reason that it does that, okay, the way you can remember this, is if I kind of block out the rest of the arrow, here's a little positive side, a little positive sign. So the positive sign goes on the positive side of the molecule, and it points towards the negative side of the molecule. All right, so that's dipole. Now let's consider the boiling points of ICl versus Cl2. Okay, ICl has a boiling point of 97 degrees versus Cl2, which has a boiling point of negative 34. Well, what is boiling? Boiling is putting things into the gas phase, right? And we know that gases happen when particles are really far apart, so they're not interacting with each other. Okay, so in order to go from a liquid where the particles are interacting with each other to a gas where they're not, you have to add energy to break all the interactions between the compounds. That's why you have to put energy in to boil water. Okay, so here's ICl, and here's Cl. There is no difference in electronegativity here. So this is a nonpolar bond. There is a difference between these two compounds. Chlorine is one of the four most electronegative, right? FOClN. Which means that there is a difference between these two atoms. And chlorine is going to be the most negative, and iodine is going to be the most positive. So what's going to happen is, if I have, let's say, one molecule of ICl here, I could get another molecule of ICl here, where the positive end of one compound is next to the negative end of another compound. And you think that seems kind of like what happens in covalent compounds. Yes, okay. There is an attraction between the negative side of this molecule and the positive side of this molecule, okay? And this is a dipole, and this is a dipole. So this is called a dipole-dipole interaction. All right, and dipole-dipole interactions are actually fairly strong. Now, something to keep in mind here is that there can be some strange stuff. All right, the shape of the molecule actually does matter. So let's take a look at water, okay, which is a liquid at room temperature, versus CO2 and CCl4, which are gases at room temperature, which means that they have very weak intermolecular forces. Here's Cl4. You'll notice that Cl4 is going to be tetrahedral in shape, CO2 is going to be linear in shape, and H2O is bent. All right. Now H2O, oxygen, is electronegative. Hydrogen isn't, So you get these dipoles, these bond dipoles forming this way, and which means there's an overall dipole pointing up from the bottom up through the molecule towards the top. Okay? So there is a net dipole pointing up through the molecule. All right? So if I get one water molecule like this, it can sit next to another water molecule like this, where you have the negative charge here next to a hydrogen that has a positive charge here. Okay? And we're going to come back to water because it's even more extreme than that. Okay? There's more stuff happening. But you look at CO2. Now, there are bond dipoles. Okay? This is these are polar covalent bonds. Okay? So this oxygen is more electronegative, right? It's one of the four most electronegative. Okay? And so you get these bond dipoles going this way. Well, if you grab your hands in front of you and make stick your elbows out as far as you can, and you try to pull your hands apart. If you're pulling as hard as you can in both directions oppositely, your hands don't move because the force that you exert while you're trying to pull out cancels out. Well, the similar thing happens with this bond dipole. There's no net dipole in the molecule. Because both of the bond dipoles cancel out. And you'll see something very similar with CCl4, okay, where there are bond dipoles, but the molecule is perfectly symmetrical, which means all of the bond dipoles are pulling out in different directions, and they all cancel out. Okay, so this would also be a no net dipole, which is why this is a gas at room temperature. Okay, so here's just another example of dipole-dipole interactions, all right, just as I showed you. So all the bond dipoles can line up, okay? You get positive and negative interactions if you switch around a bond dipole, okay? These are dipole-dipole forces, which are a form of intermolecular forces, okay? Well, what happens if you have a molecule like water and it runs into a molecule like oxygen, okay? Well, we know that water has a pretty strong bond dipole, right? So this whole side, this whole area of water has a sort of positive charge, okay? Now, the electrons in oxygen are kind of free to move about a little bit, and so they'll start to shift towards this side, which means, you know, in a normal oxygen molecule, if I were to look at like how the electrons are distributed, it's going to be something that looks kind of like this, right? But now, instead, your electron density is going to be more like this, where it's going to favor the side near the positive charge, okay? Now, if you do that, what you do is you create this really weak, kind of pseudo-dipole, okay? This is a pseudo-dipole. It's a momentary dipole, okay? And it's weaker than these dipoles, okay? But it does exist, and you can get a little bit of interactions. So this is an example of dipole-induced dipole. Okay? Now, in order to, let's say, in order to dissolve something, you have to have a liquid which interacts with the things that you're trying to dissolve. So oxygen can be dissolved in water. And we know that because that's how fish breathe. They filter through their gills, they filter out all the dissolved oxygen and they put it into the bloodstream, right? And the reason that oxygen can dissolve in water is because of this dipole-induced dipole interaction. All right, now the next one is the weakest and kind of the strangest, all right? And that's London dispersion forces. And you see this diagram in your textbook, but it's kind of hard to see in a static form. I think it's a little bit better in a dynamic form. So here's an example of London dispersion forces. Okay, you can see that as these two neon atoms approach each other, now we know that neon is a noble gas, so there is no bond that's going to form between two neon atoms. All right, so as two neon atoms get closer to each other, the electrons kind of repel away from each other. And when they do that, you get a momentary negative end of an atom, and you get a momentary positive end of an atom. And if you do that, what you've done is you've created like a momentary dipole. Okay, this is another one of those sort of, this is like an even weaker pseudo dipole. Okay, where you get uneven distribution of charge. And the side that that the nucleus is on is going to have sort of more of a positive charge. So this is more positive and this end's more negative. Okay, and if that comes in contact with another atom, okay, the positive end is going to attract electrons over to it and repel the positive end. So what's going to happen is you're going to get two atoms that have uneven charge distributions, and you get this really weak attractive force. Okay, this is London dispersion forces, and these are super weak because you would expect that this interaction to not happen for very long, right? Because electrons are constantly moving. So this is just a snapshot. This happens instantaneously, and as soon as the atoms bounce off each other, those electrons snap back, and then you're repelling again. All right? So this is a very, very weak intermolecular force. So let's take a look at boiling points and bonding types. So you can see the lowest boiling points are between nonpolar covalent molecules. So things like hydrogen. Hydrogen is a gas at room temperature, and in fact you have to go down to negative 253 degrees Celsius to get it to become a liquid. Okay, now what about something like bromine? Why would something like bromine have a higher boiling point than something like chlorine? Well, look at this from a periodic table perspective. Okay, bromine is lower on the periodic table than chlorine. So bromine's got more electrons, which means that bromine can have more London dispersion forces than chlorine. Okay? So here are polar covalent bonds. Okay? Notice that they have, on general, higher boiling points than the nonpolar covalent compounds. Okay? Then you get into something like ionic. And then even stronger than that is the metallic, the sea of electrons, right? Metallic intermolecular forces are actually very, very strong because they just form these gigantic networks. Okay? Now the last one that I want to talk about is sort of a special case. Okay, and that is, let's say, for example, water. It stands out that water has an extremely high boiling point. Okay, and that's because water can do something called hydrogen bond. All right, now if I look at water like this, okay, and here are my electrons, that's great. Okay, I know that there's a net dipole going this way through the molecule, but if I write water like this, okay, and here are the electrons being shared, Okay, you can see that there's a lot of negative charge around the oxygen, and there's basically just these hydrogen atoms are basically just protons, right? They've lost their electron, which means that they're just protons. So there's a lot of dense positive charge here and a lot of negative charge here. Not only is there a dipole here, but you can see that you have two lone pairs in their own orbitals, okay? And those orbitals, those lone pairs, are just dying to get close to another hydrogen. So what you can do is you can actually get a lone pair that recognizes this hydrogen, and you can form a kind of bond here. So this hydrogen can kind of share those electrons with this oxygen or with this oxygen. So you get these huge networks, okay? And this is called a hydrogen bond. And it is almost, it's about half as strong as a covalent bond, which means it's very strong. Okay? Now, there are only certain atoms that can hydrogen bond. And those are things that are very electronegative. You have to have a very uneven distribution of charge. So that's nitrogen, oxygen, chlorine, and fluorine. Okay, those are the only four things that can hydrogen bond. All right, and in order to form a hydrogen bond, you have to have these lone pairs. All right, so that's hydrogen bond. That's the strongest intermolecular force, and we'll use intermolecular forces a lot.